So we're talking about Newton's law of gravitation. What Newton's law of gravitation tells us is that all objects in the universe attract one another. So right here I have a Kleenex box and I have my remote to the projector. Is the Kleenex box a mass? Yes. Is the remote a mass? Yes. So what do we know about these two masses? They are, even though you can't see it or even feel it, what do we know to be true about these two masses? They're attracting each other. All objects in the universe attract each other. This is Newton's law of gravitation. Now, there's an equation for it. The equation for finding the gravitational, we refer to the force of attraction between masses. It is a gravitational force of attraction. So notice the little sub g right here, force gravitational. It's equal to big G, which you have not seen this before. Don't confuse the big G with the lowercase g. Lowercase g would be acceleration of gravity. This big G is what we call the gravitational constant. Now I just want to draw your attention to something. Look at how small the gravitational constant is. 6.673 times 10 to the negative 11. So let's say we got two small objects, just, a 1 kilogram mass and a 1 kilogram mass. Like, here I have a 1 kilogram mass and a 1 kilogram mass separated by 1 meter. You're not going to notice the force of attraction because, look, when you plug into this equation, the gravitational constant is 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7, 3 Newton meter squared over kilogram squared. Let's say that the first mass is 1 kilogram, the next mass is another kilogram, and they're separated by 1 meter. Is this going to give you a noticeable force? No. And the reason is the gravitational constant is too small. So, in order to get a noticeable force here, in order for this force to be noticeable, what has to be true about one of these masses? Not both of the masses, just one of these masses must be what? Incredibly large. And am I talking like the size of my car large? No. Am I talking like the size of my house large? Even bigger. What type of large am I talking about? Like a planet, like the Earth. Okay, so let's say that the Earth is m1, and by the way, we do know the mass of the Earth. It'd be given. Let's say the Earth is one mass, and then this Kleenex box is another mass. Would there be a noticeable force between the Earth and this Kleenex box? Let's just make sure. Let's just see. Ready? Yep, there was a noticeable force there. As you all saw, the Kleenex box got pulled down to the Earth. Okay? Okay, a couple things. So look over here. In this equation for finding the gravitational force between two masses, so I have a diagram here. We have a small m1, so we're looking over here now. We have a small m1 and a larger m2. These masses will attract each other. m1 is attracted to m2, and we'll label that as Fg for gravitational force. It's a gravitational force of attraction. And then this is gravitational force. So m1 is attracted to m2, and m2 is attracted to m1. But here's the catch. m1 is smaller, and m2 is larger. Will these two forces be the same or different? How many of you say they'll be the same? How many of you say they'll be different? Okay, only about 4 people. Who says they're going to be the same? Yes. Who says they're going to be different? No. They're the same. Now, in fact, Newton has another law for why this is true. It's called Newton's third law. Remember what Newton's third law is? Every force has a equal and opposite reaction force. So this is a perfect example of that. Perfect example of this. The small guy, m1, exerts a force on m2. That's this force right here. m1 exerts a force on m2, and then what's m2 doing to m1? Exerting a force back. These guys are exerting a mutual force on each other. They're mutually attracted to each other. It's just like you sitting right in this room. Look, is the earth pulling you down? Yes. Praveen, look up here. The earth is pulling you down, so what else must be true? You are pulling the earth up. Those two forces are equal. Even though you're small and the earth is big, the force that you exert on the earth is equal to the force that the earth exerts on you. Every force has an equal and opposite reaction force. Okay? That's a very common question because kids look at this and they're like, oh, they start thinking the forces must be different because one is big and the other one's small. Okay, another thing I want to point out here, in this equation, R is from center to center, right? From the center, this is going to be important in a minute. From center to center. From the center of M1 to center of M2. All right, now, there are two applications for Newton's law of gravitation. The two applications are, first one, finding the acceleration of gravity on or above a really large mass. And look, at the end of the day, this is the equation that you're going to be using. But guys, do I want you to memorize that equation? No. What I would prefer is that you know how to figure it out, which is what I'm going to show you right here. It's very simple. Okay, who wants to be my volunteer? I'm going to send you on a rocket way far away from the Earth. Who wants to be on a rocket way far away from the Earth? Okay, Reed. Reed is going to be, it was like that, who was that guy? The Red Bull guy who jumped out of that balloon, like set the record for highest skydive. What was his name, Rufus? Felix. Felix. Okay, so here's Felix, guys. Felix. No, it's Reed. Sorry, Reed. It's Reed. Here we go. We got Reed. And Reed, you're going to be M2 because the Earth is bigger, so we're going to call the Earth M1. Now, the important distance here, the important distance is from the center of the Earth to center of Reed. So that's R. Now, dudes, this is very simple. What we're trying to do is we're trying to figure out the acceleration of gravity way high above the surface of the Earth. What happens to the acceleration of gravity as you leave the Earth? It gets smaller exponentially, right? Because R is squared. So for example, what if you double your distance from the center of the Earth? If you double R, what's going to happen to gravity? Times 1/4. What if you triple R? Times 1/9. It'll be, right? It's exponential. Okay, so how do we figure out this equation? Because you have to know this equation. Rather than just memorize it, I would like you to understand where it comes from, and it's very simple. Look, so Reed is attracted to the Earth, right? And that is a gravitational force of attraction. And by the way, guys, is the Earth attracted to Reed? Yes, right? No force exists in isolation. If Reed is attracted to the Earth, that means the Earth is attracted to Reed. Now, guys, what was the first equation? What was the first equation that you ever learned for force of gravity? Going way back to like September. mg, where this would be what? Mass of Earth or mass of Reed? Mass of Reed, because we're focusing on Reed here, right? We're focusing on this point up here, okay? So the gravitational force on Reed is equal to mass of Reed times the acceleration of gravity. But what I just showed you today is there is a second equation for the gravitational force between objects. What's the second equation? Big G, M1, M2 over R squared. There are two equations for the force of gravity. So you set these equal to each other. Sorry, Reed, what happens to your mass? It cancels. So it doesn't matter. It doesn't matter if this was Reed or a bag of potato chips or a tennis ball. It doesn't matter what it is because it cancels out. M2 cancels out, and notice what you're left with. You're left with this equation. So guys, let me ask you a question here. What if you had some unknown planet? Let's say you're on the AP exam. Let's say that you're on the AP exam and they give you a planet, okay? And they want you to find gravity on the surface of the planet. What two things would you need to know to find the acceleration of gravity on the surface of the planet? Yo.
The mass of the planet.
The mass of the planet
The radius.
and the radius of the planet. If you know those two things, you can find gravity on the surface of that planet. Okay, second application, and then we're done. Okay, the second application for Newton's law of gravitation has to do with one object orbiting another object, like the moon around the Earth, or the Earth around the sun. And I just want to mention, by the way, both of those things that I just mentioned are actually elliptical paths. You guys know what an ellipse is? It's a circle that has been smushed, and there's different degrees to an ellipse. They call that what, the eccentricity. So guys, for this class, do you want to know what we're going to do for elliptical motion? We're just going to say, it's close enough to a circle, okay? And that's, okay, that's College Board approved. We are going to say that this orbit here, this orbit, we're going to call it circular. So say that this is the moon, so we'll call this M2, and then the Earth is M1. Now guys, we're going to look at forces right now. So what does this V represent? This V is the tangential velocity of the moon around the Earth. Okay, now what distance will be important? In fact, hold up. I'm going to erase this velocity because we're going to look at forces. I'm going to erase the velocity because we're not concerned with that right now. The distance that we're going to need is from the center of the Earth to the center of the moon, R, right? Now, is the Earth an object? Yes. Is the moon an object? Yes. So these forces are gravitational forces, right? It's a gravitational force of attraction. Now look at this. Look right here. What is the only force acting on M2, which I'm saying is the moon? So focusing on M2, if we sum the forces, what's the only force acting on the moon? It's the gravitational force. Notice that the gravitational force points to the center of this circle. For an object that's in a circular path, what type of acceleration is that? Centripetal, which is caused by a centripetal force. So when you sum these forces, the only force acting on M2, if you focus in on M2, the only force is the gravitational force. Sum of the forces equals MA, where this would be M2. This is a centripetal, because it's in a circular path. Now, we're ultimately going to end up with this right here. We're going to end up with this. Now, what is the equation for gravitational force? Big G, M1, M2 over R squared, okay, equals M2. Now, what's the equation for centripetal acceleration? Centripetal acceleration is V squared over R. Now, this cleans up rather nicely. The M2 cancels. One of the R's cancels. And what you get is V squared equals G, mass of the Earth, over R, which is the same thing as this equation. And what's this V? So going back to the beginning, what's the V? So if you look at this satellite right here, this moon, it has what we call a tangential velocity. And this is how you would find it. Does the satellites, does this moon, or whatever it is, could be a satellite, could be a moon, does its velocity around the Earth depend upon its mass? What's this M in this equation? Is it the mass of the satellite or the mass of the center guy? It's the mass of the center guy. Notice that the mass of the satellite canceled out.